CMOS NAND to 2-input NAND gate. Figure shows a 2-input CMOS NAND 2 gate. The operating principle of this circuit is exact dual of CMOS NOT 2 operation examined earlier. The NNet consisting of two series connected NMOS transistors creates a conducting path between the output node and the ground only if both input voltages are logic high, that is, are equal to VOH. In this case, both of the parallel connected PMOS transistors in the P net will be off. For all other input combinations, either one or both of the PMOS transistor will be turned on while the N net is turned off, thus creating a current path between the output node and the power supply voltage. Here you can see in this figure parasitic device capacitance of the CMOS NOT 2 circuit and a simplified equivalent with the lumped output load capacitance. Using an analysis similar to the one developed for the NOT 2 gate, we can easily calculate the switching threshold for the CMOS NAND 2 gate. Again, we will assume that the devices in each block are identical with the W by L NA equal to W by L NB and W by L PA equal to W by L PB. The switching threshold for this gate is then found as VTH NAND 2 equal to VTH plus 2 root over Kp by Kn VDD minus mod VTP by 1 plus 2 root over Kp by Kn. Here you can see the figure a CMOS NAND 2 gate and its inverter equivalent. As we can see from equation, a switching threshold voltage of VDD by 2 for simultaneous switching is achieved by setting VTN equal to mod VTP and Kn equal to 4 Kp in the NAND 2. At this point, we can state the following observation about the area requirements of CMOS combinational logic gates in comparison with equivalent NMOS depletion load logic. The total number of transistors in CMOS gates is about twice the number of transistors in NMOS gates, 2n versus n plus 1 for n inputs. The silicon area occupied by the CMOS gate, however, is not necessarily twice the area occupied by the NMOS depletion load gate, since a significant portion of the silicon area must be reserved for signal routing and contacts in both cases. Thus, the area disadvantage of CMOS logic may actually be smaller than simple transistor count suggests. Layout of simple CMOS logic gates. In the following, we will examine oversimplified layout example for CMOS NOT 2 and NAND 2 gates. Figure shows a sample layout of a CMOS NAND 2 gate using single layer metal and single layer polysilicon. In this example, the P-type diffusion area for PMOS transistors and N-type diffusion area for NMOS transistors are aligned to allow simple routing of the gate signals via two parallel polysilicon lines running vertically. Figure shows the layout of a CMOS NAND to gate using the same basic layout principles as in the NOT 2 layout example. Here you can see in this figure simple layout of the CMOS NOR 2 gate and figure sample layout of the CMOS NAND 2 gate. Its layout style allows the so-called free-through of signals in the standard cell layouts for signal routing among multiple standard cells. The feed-through feature provides area savings in signal routing for without it, as in the case of NMOS standard cell. Separate feed-through cells need to be inserted just for signal routing purpose. Here you can see in this figure stick diagram layout of the CMOS NOT 2 gate. Finally, figure shows a simplified stick diagram view of CMOS NOT 2 gate layout given in figure. Here the diffusion areas are depicted by rectangles and the metal connections and contacts are represented by solid lines and circles respectively, and the polysilicon columns are represented by cross hatched strips. The stick diagram layouts does not carry any information on the actual geometry relations of the individual features, but it conveys valuable information on the relative placement of the transistors and their interconnections. Thank you.